Welcome, students! In this video, we will learn about sound. Let's start with vibrations. Sound begins with vibrations. Imagine speaking or strumming a guitar. Your vocal cords or guitar strings vibrate, moving air molecules around them. This movement creates sound and makes the air molecules shift. But sound needs something to travel through, and that's called a medium. It could be air, water, or even solids. In space, there aren't enough particles for sound to travel, so it's silent out there. As vibrations happen, they cause particles in the medium to move closer together and then farther apart. This creates a pattern of high and low pressure areas called compressions and rarefactions, forming sound waves that spread through our world. Sound waves travel outwards in every direction from where they started. They carry energy from the original vibration reaching our ears. Sound travels at different speeds depending on the medium. It goes faster through solids than liquids, and even faster through gases. So, if you shout in water, it would reach someone faster than if you were yelling in the air. Let's understand how sound moves. Sound waves are longitudinal waves. This means the particles in the medium move in the same direction as the wave. Next, we have waves. Waves transfer energy and information without physically moving the particles from place to place. The two main types of waves are transverse and longitudinal. In transverse waves, particles move up and down or side to side while the wave moves forward. For example, when you shake a rope, you create crests and troughs that travel along it. Longitudinal waves, like sound waves, have particles moving back and forth in the same direction as the wave. They consist of compressions and rarefactions. Moving on, let's discuss the characteristics of sound waves. A sound wave is a mechanical wave that moves through air by vibrating particles. When something vibrates, it creates areas of high and low pressure that combine into a sound wave. When these reach our ears, they make our eardrums vibrate, and our brain interprets this as sound. The wavelength of a sound wave is the distance over which the wave pattern repeats, shown with the symbol lambda, L. Amplitude measures how large the wave is and tells us how loud the sound is. A larger amplitude means a louder sound, and if the wave size doubles, it can sound 4 times louder. The time period is how long it takes for one complete wave to pass a point, marked with the letter T and measured in seconds, S. Frequency tells us how often waves occur in a second, measured in hertz, hits. Higher frequencies create higher pitches, while lower frequencies produce deeper sounds. The speed of sound depends on the medium's properties, like density and elasticity. It travels faster in solids and slower in gases. Pitch refers to how high or low a sound seems and is linked to frequency. Higher frequencies result in higher pitches. Quality or timbre makes sounds unique and allows us to tell different instruments apart, even if they play the same note. The speed of sound changes with various factors. It moves faster through dense and elastic materials, quicker in solids compared to liquids or gases, and faster in warmer environments because particles are more energetic. Humidity, pressure, and altitude can also affect sound speed. Sound can bounce off surfaces, a phenomenon known as reflection. When sound bounces back after hitting a surface, it creates an echo. You can hear an echo if there's a delay of at least 0.1 seconds, often in large spaces like mountains or empty rooms. Reverberation occurs when sound continues even after the source stops, bouncing around in enclosed spaces. We use echoes and reflections in cool technologies like sonar and ultrasound. Sonar sends out sound waves underwater that bounce back after hitting objects, helping to map the ocean floor or find ships. Ultrasound uses high-frequency sound waves to create images of the inside of our body, allowing doctors to check on babies before they arrive. Our ears are incredible. They have 3 parts: the outer ear, middle ear, and inner ear. The outer ear, or pinna, collects sound waves and directs them into the ear canal. The middle ear contains 3 tiny bones called ossicles that transfer sound vibrations to the inner ear, which converts them into signals for the brain. Now here is a question for you. What do we call the distance between 2 consecutive compressions in a sound wave? Please share your answer in the comments. The complete curriculum for Class 9 is available on our channel. Check out all the links provided in the description below. Please make sure to like, share, and comment for more such videos.